Hello. Hi. First session of the conference. What can go wrong? Okay, hi everyone. Thanks for coming here. I guess we're ready to start. Is the Zoom webinar ready to go? Is it all fine? Okay, thank you. Well then, I'm going to start with introducing ourselves. We are Dynamic Cast, and for those of you who don't know us, we're a peer-to-peer study group for people underrepresented in tech. We started off focusing on the C++ programming language, hence the logo. And in our meetups, currently happening mostly in person in London and also online, we meet at Focusrite offices. Thank you, Focusrite. We usually meet to share something we've learned or share our projects or also brainstorm talk ideas and prepare proposals together. So if you'd like to join us, speak with us later. So today's talk has been a collaborative effort of the people you can see listed on the screen. So let me introduce you Harriet Drury, a software developer at Native Instruments working on AI-enabled isotope products. We have Julia Läger, a software developer and manager from Focusrite, our today's Jupyter notebook expert. So you know who to direct questions to. We also have Sohyun Im, currently pursuing her master's in sound and music computing at Queen Mary University of London. We have Pauline Nemchak, a software developer specializing in web technologies and UI and UX design. And myself, Anna Wszeborowska. I'm a software developer currently working as a part-time contractor in music tech and a part-time academic researcher on a project focusing on responsible AI for music. Okay, so there will be some links on the slides, so if you'd like to follow through, you can go to our GitHub account, to this workshop's repository, and we have slides uploaded in the wiki page. We'll be going through the repository today during the workshop, so it's good to have it open anyway. Okay, so let's just briefly, I don't know, for those of you who haven't read the description, maybe we'll repeat it. For those of you who haven't, I'm just going to briefly mention what we will be going through today. So we would like to demonstrate a practical example of using machine learning in an audio application. We have created a prototype application for you. Bear in mind, it is a prototype. It will sometimes crackle, and it will have some anti-patterns there for making real-time audio applications. But it's an interactive prototype in Python that connects well with machine learning tools in Python, and we can just have this workshop in an interactive way, which we thought was a good idea. So we will show you how you can use an existing generative model and embed it in your application, and then we'll walk you through the stages of training a different model. And this other model will be used to control the generative model. So we will basically show you how to define your own custom gesture control of the generative model. Okay. So just to make sure, there's going to be a little bit of theory to set the scene and make sure we're all on the same page. So for those of you who sometimes maybe are confused with the term machine learning, how it differs from AI, widely used, is that machine learning is a subset of artificial intelligence that focuses pretty much on algorithms which make sense of data, right? So you feed it some data and a machine learning model figures out patterns in it, so you don't have to explicitly program your applications. Just curate the data you feed it and choose the right application, architecture. Right, and what are generative models? Well, generative models are these machine learning models which have the ability to generate new data, ideally that nobody has ever seen before, the sounds you've never heard before, and so on. So generative models try to understand patterns and structures in the data that were fed. And yeah, we call this data a data set. And yeah, they generate new examples similar to the data you fed it. So where do we see AI music generation used these days? Well, I like to divide the use cases in these three categories. We have seen coherent song generators, right? Some well-known models that know how to generate 3-minute-long songs with sometimes lyrics on top of them. And we have what I like to call sample generators. So these models generate shorter sequences. Sometimes these are sound effects or percussive samples. You have quite a few of these existing already. And the third category, which is what we like to focus on, would be instruments. And what I consider an instrument would be a model which generates output in real time, so that you can interact with it like with an instrument. So you can hear, you can interact and hear the effects of this interaction instantly. And so they would be able to generate an audio buffer at a time in real time. And this is what we will be dealing with today. Okay, so what can sound be generated in response to? I'm sure all of you have already seen the models that take text as input, so we can prompt our output with a description of what we want to hear. There are some existing solutions where you can select a set of features that determines what the output will be, and these could be a musical style, mood, tempo, and so on. There are some models that work with no input. So if you imagine like a model that generates percussive sounds, and you just say, generate me kicks, and you have a button that says generate, and you keep generating until you find something you like. That's also an option. Or there are models that take audio as input, and then they generate sound. So yeah, you pass an arbitrary audio file, and then they will pass it through your trained model and generate the output in the style of the training data that this model was trained on. And this kind of a technique is called usually style transfer. Style transfer is a term that comes from computer vision and graphics, but we have adapted it to the audio domain as well. And in the audio domain, it will also sometimes be called timbre transfer or timbre transformation. This is also what we will be doing today. That's why we're introducing this term, so that you understand better what's happening. Okay, so how can we interact with generative models in musical contexts? If you think about it, it's actually not so trivial to define a meaningful interaction with a generative model. Well, for many reasons, but one of them is that models have such a vast parameter space that it's, first of all, hard to decide which parameters to expose. Secondly, how do you even label them, right? How do you make sense of them? How do you group them? So that's still a very active field of research currently, interfaces of AI-based instruments and effects. Right, and it is also important to distinguish between, are we using generators or instruments, right? When it is an instrument, you may be interested in something we call embodied interaction. So you basically use your hands or gestures or want to turn knobs, right? So again, it is not trivial to know what to expose and how to map these parameter spaces in a way that feels meaningful to the user and also maintains the sense of agency. They want to feel like a musician, a creator, right? Not just somebody who's fed an arbitrarily generated sounds. Right, so let's just briefly cover the common challenges associated with building generative models. Well, there are many. We've listed a few here. First of all would be, well, dataset collection has been a pretty hot topic these days because of the copyright issues. So if you want to create a very large model like Pseudo and UDO, you have to have access to a very large data set that you may or may not ethically source. When you deal with smaller models that you can train on your own collections, then that's a bit easier. Because also, first of all, you're the owner of the data you're training on, and also the training times are gonna be smaller, so like you're gonna train faster and it will require less computing power. Also, still dealing with this kind of technology requires pretty good technical literacy. So it's not so easy for musicians most of the time to jump on this technology and learn how to train models and generate new sounds. And then all of the above kind of tied to ethical considerations around using the technology because of the copyright issues, as I mentioned before. Also, the large language models that are trained on these vast data sets are going to have a lot of inherent bias. And what I mean by this is that they're mostly trained on, the kind of data that's widely available, which is mostly Western classical and pop music. And this further marginalizes underrepresented styles. And the consequence of that is also cultural, right? Because it's up to us how we curate our culture. There's also an environmental and financial impact of training very large models that is also an issue widely discussed these days. And it also means that when we depend on large data sets, a lot of money to be able to train in the cloud, and then it means that the access to this technology, especially for training very large models, is restricted to big companies. So even universities many times cannot afford it. So, but this is when it comes to very large models, people working on smaller models and different techniques try to address these issues. Just something to be aware of. Okay, so let's move on to part one of our practical workshop, in which we will be embedding a generative model in a music application. So as I said before, we have prepared a prototype of an audio app for you, which applies a slide transfer effect we talked about earlier to sample an audio sample that we loop and play in our sampler. We will be working with this app throughout the workshop, so and we will be recreating parts of it. So I think it will be good to first see what it does. So now I'm going to hand over to Pauline for a quick demo of the first part of the app and a brief overview of this app so that you know what you're dealing with.
So I will show the demo of what we're going to do in the first part of our workshop. So we have this web UI application, and what we have is 4 faders that help us to navigate latent space dimensions, and we have 3 buttons that well, you can understand by icons what they do. Like we have first play button, then second button is to play it on repeat, to loop the sound, and the last third button is to transform the sound. So I will try playing it. So this is the original sound, and now we will try to transform it. as you can hear, it was it's like percussion based model, as you can hear by the sound. And do I just?
Yeah.
Yeah, and about the application, just general information. As you have seen, it's a desktop application, but it has a web UI. A desktop, it means that we don't actually do anything in the browser. We just draw the interface that you can communicate with, but you don't do anything with audio in there. The application itself is written in Python using Flask framework, Python framework. Audio, as I said, produced and transformed locally. And also the important part is that audio engine runs in a separate thread, so we won't have any problems like freezing or anything else because the audio is like in a separate thread, and it won't interfere with the UI interactions. And in more detail, Anna will continue.
Thanks, Pauline. That sounded very experimental, but it's like trained on percussive sounds. Depending where you go with the sliders, the sounds may be very different. So I hope you see it later as well. Okay, so maybe we will be now explaining what this app does. So again, just to remind you what it does. Applies like, there are some wild sounds in this. Yeah, it really depends where you go. This sound is really weird, by the way. Well, like, it depends where you go. You can just find some hi-hats somewhere, some low tones, some derbuka sounds. Depends. Anyway, let's see what the technology sitting within this app is. So basically, we are using a model called RAVE, that stands for Real-Time Audio Variational Autoencoder. It's a model that got developed at IRCAM, and it enables a fast and high-quality neural audio synthesis. So basically, you can train this model on your own sounds. You roughly need 3 hours of audio to train a model, and it trains for a few days in the cloud. But then you can perform real-time inferencing, so you can basically use it as an instrument. Even though this sounded like muffled sounds and so on, it actually generates output in like high-quality sampling rates, as opposed to other models dealing with, that use like low-resource models and smaller data sets. And there are also a lot of tutorials and helper tools available to support training your own models. So this is why this model has become very widely used by people in the field. And you have a lot of different models to try with it. Okay, so this model's architecture is called Variational Auto Encoder. And what the main properties of this model is that it can, as any generative model, can learn important properties of the data it was exposed to, and then use this knowledge to generate new sounds, right? And it can also be controlled, and we'll see why in a second. It has these properties that that make this model easy to control by end users. Okay, so in order to understand how variational autoencoders work, it's going to be easier first to start with autoencoders, which is a type of a model VAEs are derived from. This is not the model we will be implementing, so you don't have to understand it in detail, but there are some theoretical concepts which hopefully will make it clearer what we're doing within the app. So first of all, autoencoder is an encoder-decoder architecture. which basically means that there are two networks that are being trained together during the training time. So encoder takes an input and basically compresses it to a much smaller representation, and we call it the encoding. And then this encoding is being passed to the decoder, and this decoder can convert the encoding back into the original input. And this is what happens during the training phase of an auto encoder. So basically, in essence, autoencoder architectures learn how to compress and decompress information. You can just think about it intuitively as kind of a lossless compression algorithm. Right, so what are the conclusions? That the encoding contains enough information for the decoder network to reconstruct it. And in order to achieve that, encoder learns the most important properties of the input data and somehow manages to discard the irrelevant parts. Okay, so if we were to represent it in a picture, this is what it could look like. This is your audio data buffer of whatever size you decide it should be. Let's say it's 512 samples, and then you pass it through the decoder, and your embedding can be as small as 2 numbers, right? So you just perform this kind of a compression of data, and it turns out that just these 2 numbers is enough to represent your input data uniquely enough for the decoder to be able to deconstruct it. So let's see how that happens. Also, the embedding is sometimes going to be called bottlenecks, so you can see these names used interchangeably in some literature. So basically, when we pass our input data through an encoder, the embedding is created in something called the embedding space, which is also called latent space. In this example, the latent space is 2-dimensional. So basically, each embedding in the end represents a coordinate on this latent space. So basically, the encoder decides, okay, this sounds like I want to place it somewhere in the middle, right? And its embedding is going to have numbers like, I don't know, 0.5, 0.5. And this is basically a coordinate, right? And you place it there. And the autoencoder also learns to group similar features close to each other. Okay, so in our example, we had a 2-dimensional latent space represented by 2 points. If we have a 3-dimensional latent space, you would have the coordinate described by 3 points. For 4-dimensional latent space, 4 points, and so on. So in our example, we had 4 sliders letting us control 4 latent dimensions, which, these were basically representing a latent space coordinate, a 4-dimensional latent space coordinate. Yes, and each latent space dimension corresponds to a specific feature or characteristic learned during the training process. So if you start playing with the app, you may hear that one slider will act like a low-pass filter maybe, or the other will just go from, it's very hard to sometimes describe these features. Sometimes they correspond with an actual DSP filter you're used to, and sometimes it's just something else it figures out, which is hard to describe with words. That's why labeling is hard. Okay, so let's summarize again what the encoding phase does. So yeah, when you pass your audio input through an encoder, it places it on the latent space and assigns coordinates to it. So the embedding are the latent space coordinates. During the decoding phase, we just sample a point from this latent space and pass it through the decoder. And the decoder should be able to reconstruct the input data precisely. Okay, so that's all good, but autoencoders are usually used for reconstructing data. They're used for denoising or for compressing and decompressing the data later, so storing their compressed representations. But when you want to generate novel sounds, you would actually want to sample from the gaps in the latent space because you want to hear something nobody has ever heard before. You don't want to reconstruct the input that was fed during the training process. And this is what autoencoders don't let you do. And it is mostly because the latent space is organized in clusters of similar things close together, but this space is not continuous. So, which means you cannot just navigate through it smoothly and interpolate between different sounds. So, in order to generate novel sounds from the gaps, we need to use variational autoencoder. Why? Well, because it introduces two tricks that makes it possible. First of all, in VAEs, the latent space is continuous by design, and the latent space is centered around the origin, around the 0, 0 coordinate. How is it achieved? Basically, instead of basically embedding something into a single coordinate, you just create an embedding from somewhere in this probability distribution. And when during the training, each time you pass in the same input, you're gonna sample from, you're gonna put the points in a slightly different place. And so then the embedding is not one single vector, it's actually two vectors, one vector of means and one of standard deviations. And then, since you keep putting this embedding somewhere within this circle, the decoder learns that not only a single point in the latent space represents the input, but also all nearby points refer to it as well. And thanks to it, it just learns how to generate sounds that they're slightly vary, but are similar enough. And centering around the origin is achieved by also, during the training phase, penalizing, putting the similar clusters far from each other. So thanks to that, all encodings just end up evenly distributed around the center. And then if we optimize for both reconstruction loss and this divergence loss, we end up with a latent space that has similar clusters next to each other locally, but globally it's densely packed within the origin. And then thanks to that, we can basically navigate this space easily. So in our application, when you see these like 4 sliders that are ranged, right? We had to just choose some values for this range. So we basically are cutting off a part of the latent space around the origin. And this is our range. Okay, so how do you navigate this latent space? As we've said before, you can just choose one place in a latent space, sample from it, and you can just move around by adding or subtracting from this vector. And this is precisely what we're doing with these sliders. Right, so basically, again, you pass when we are playing back our sample, we pass one buffer at a time. This buffer goes through the encoder. Then we have the embedding. We manipulate it with the sliders and pass it through the decoder to hear the output sound. This is basically what's happening. So now let's interact with the app from Jupyter Notebook. I'm gonna pass on to our Jupyter Notebook expert, Julia. No pressure.
Hello. Hi. So now we had lots of theory. We can go. I hope the room in 20 minutes will be very, very noisy. If it will be, I have succeeded. So if you want to get started with it, you can go to our repository here, and I set up a minute way to set up this notebook. And we can go through it together now, if you're ready. And I'll be with you. I will actually try to do the same thing as you do. So this is our Flask app running. I will stop it now. So here's, by the way, this is the code of our repository. And yeah, we will go setting up the playground. And because
It's Python-based. It'll be easy. That's what I think, not everybody else. But hey. So, so first thing, if you haven't done so yet, let's clone the repository. You can also go to the to the link here on the slides. So maybe I give everyone some time, and you can just have a look at the setup there, copy paste over everything in your terminal. Cool. And if you have any questions during the setup, feel free to raise a hand. I think so some of us will be going around. Harriet's over there. Cool, Harriet can help you. Alrighty. So, do you think you all got the repo downloaded? Yeah, nice. I see thumbs up, I see interaction, I love it. So, first one, we have a two-part two parts in this workshop, and we don't want to have any spoilers for the grand finale. So could you please check out this part 1 branch? And if you have done so, we can go start to set up a local environment in Python. So I will be brave and delete my workshop, and I'll do it with you. And I might regret it later. But I've tried to set this up so many times, it should work. Okay, are you sure? I'm not, I will delete it. Okay, here we go. So, and basically I always recommend working with Python, always use a local environment, because otherwise you'll just maybe mess up your local setup. You have full control over all the modules that you have, all the versions, and it will not mess with any other Python projects you may have. So that's what we'll be doing now. So I already know my Python version. Let's go down here. Wow. Sorry, that's my first issue. What have I done? Oh, let me actually exit the environment because I deleted it. Let's just go to a new terminal. Oh, entertaining people, great. Live coding. Hey, so I have 3.12. So anything between 3.8 and 3.12 will work. So if you can quickly check your version, if you don't have that, you might need to download another version. Just raise your hand, and I hope Harriet will help you with that. And the reason why 3.13 does not work yet, because NumPy, it's not supporting NumPy. Well, tough times. All right. Okay. So I'm going through creating the workshop environment with you now. So I'm on Python. It's very similar if you're on Windows. I think the only difference will be how you activate the workshop environment. I think everything else should be the same. I'm on Mac, so I'm sorry. I tried to do it on my Windows computer, but it died a long time ago. I had good intentions. Okay, so now I'll create the workshop environment. Bloop. Now I can activate it here on Linux or like any Unix. I can do this to activate it. On Windows, you run the bats with it. Cool. So now you should have in front of your command line. Should have the environment name in front of it after it's successfully activated. So now we can just install the requirements. And that'll take some time. So if anyone has any questions now, we have quite a lot of different different modules that we're using. I hope everyone's fine with the connection. Oh yeah, also like if you have an IDE, if you have it open in an IDE now, so you can also just click it here. It's also nice. Just like in a communal spirit, I'll put it everything in the terminal anyway. Yeah, that's the last bit that always takes a little bit. I think I answered your question. As I like it sometimes, but as you can see, I don't use it to set up the environment, especially for that reason. I don't like setting up the, I'm a command line person. I like it for like PyTest stuff, debugging and all that. I use it mainly for that. So I'll pick the features that I like. Yeah, of course I could like set up the environment through the IDE. I never do it, even if I'm not doing a workshop. Alrighty, I've got my environment. So now, because we're using Jupyter Notebook, we need to make this environment available to it. And there's this command we can run, which will just make this environment available as a kernel for the Jupyter Notebook. Cool. So that was quick. Now we're going to run the Jupyter Notebook. So that should all work. Yeah. And also, like, if you have problems in between, I also like try to like see like if there's any troubleshooting, to try to think of all the things that might go wrong. Have a look at the README. There might be answers in there. Alrighty. Cool. And oh my God, where does this come from? Emma is the first to set up. I think you should win a prize for that. No, yeah, Emma's already way ahead of everyone else. So we open the notebook now. Cool. So these will be the lines that we'll try to execute. You'll be able to hear it's basically accessing the engine that's used in the web app. So we go more into detail into the code a bit later. So we have that to, just have like a really rough overview about how the audio engine works and how you can create it. Cool. So first things first, I have this this way of downloading the model. So I'll just retrieve it from here. It's the same thing that's also in the setup notes. If that doesn't work for you, you can download it manually and put it in the root folder of the project. Oh, that was quick. Wow, usually takes longer. And as you maybe know, the darbuka is a percussive instrument. Thus the percussive sounds. Cool. So after we have that, there's also like if you're a Mac user, if you want to use URLlib, you might need to install SSH certificates. There's also like a guide in the notebook setup instructions. Up to you if you want to try that or if you want to download it manually. So I show you now, so I just have it here in the root of the project. And if it's there, I'll be able to access it. Okay, now to the exciting part. Yeah. I will create the audio. I will import the bits. It takes a bit longer because in the init files are used by the Flask app. And this actually already creates an audio engine, which, because Flask does not like to share its source code with audio developers who want to access it through a notebook. Cool. And now we can create the audio engine. So the fun bit about this line is you can switch out the input. If you have any WAV file, you can try that. Also, if you go to this to the website, there are also other models you can try. So whenever you create the engine, you just swap out those two files. If you put your the file path, if you put your files in the root, it should just be able to access it. And now I'm gonna make some noise. I hope it's the output is not that loud anymore, but okay. Great. So, first things first, we go to the bottom. The most important line is this one, because this stops the audio output, right? So, and since we only started one, so if you want to start playing it again, you set stop clear. Just starting it will play it back once. If you want to loop it, if you want to loop the sample, you can set the loop, right? And and you can set the transformation with the transform set, and you can revert it with the transform clear. And here, through setting the coordinates, we'll be able to manipulate the coordinates in the latent space, as Anna explained earlier. And yeah, so we have these things that also, we have these commands basically that work well with a web socket from that the Flask app is using. So it's like why it looks like this. Okay, let's make some noise. Cool. Oh, so nice. Okay, it's looping. And now I can change the coordinates here too. I love that it's so loud. Let's live it. It brings me back to experimental music concerts, you know. So you can do it here, or you can do this. Try it out. So basically, this is just the faders. And I will stop it again. So, yeah, there's a question over there. Yeah, that's I don't know where they are. But you can hear it on your own laptop, hopefully, if the setup works. It does sound better. It does sound better. Yeah. No. I have no control. I'm at the mercy. Cool. Yeah, so what else is there to say? So just arbitrary. So I think coordinates that make sense are between -5, +5. It's like from the setting of the app. So yeah. And also, I'd really recommend if anybody has like a fun audio, like a WAV file, to just try it out. You could try it out now. Create a different audio engine.
So the original,
Yeah, the original, like the without the transformation applied.
string.
Yeah, that was a hard. It was chosen because it's like a bit like it's melodic. It's a very recognizable pattern, and you can actually recognize the source a little bit when you apply the transformation, because you have like all the semiquavers and with this like waveform with the two phrases. So if you really listen to it, to the transformation, you can like recognize the original a little bit. Yeah.
I still haven't figured out why that sounds like African.
That is the training model. It has been trained on a Dabuka, which is... Oh, yeah. No worries, no worries. So that's like I recommend listening to Jabuka music. It's good for dancing. Anyways, just facts here. Do we have any other questions?
You mentioned the modeling a lot. So take a couple of days to train.
Yeah, I think like this model that we just downloaded, I think this would have to quite some time. I'm not exactly sure how long, but this is a big model. And this is like one example of how we can utilize existing data for our projects rather than having to train data ourselves. As Anna said, it's actually like also quite high quality. Also, if you don't hear it now. So actually the audio output is quite high quality that you wouldn't achieve if we were to train it ourselves now, because like we don't have the time. Yeah. Any more questions? If not, I will hand over to Harriet, and she'll be going more into detail with you about this model. Do you want the speaker notes?
No, oh my god.
Yeah? Okay, cool. I could mirror it again. So.
Don't worry, we'll sort out on the break, yeah. Hello everyone. My name's Harriet. I'm sure a lot of you have seen me around the conference before. You've been a great audience so far. Thank you so much for all these technical problems. It's the first session of the workshops of the conference, so how many devs does it take to get audio out, right? We're aware, so this first half's been very theory intensive, and it's we're getting through the idea of a rave model and all the bits there. We will be training later, I promise. So to go back to what Yulia was just saying, actually, we picked the rave model because we found that we can interact with it quite easily. It's got a nice community around it, and it's all open source, which is great for workshop content because we can freely set up all of our code and everyone is free to go from through. So what we were just doing then is called inference. So we weren't training, obviously, we were just playing with the model, so we were just getting a sound, we were getting that nice percussive harp, we were playing with our latent dimensions, and then we were getting some nice Jabuka drums. Not so nice out of these speakers, but they are nice, I promise you. So what I want to cover quickly before we break and let everyone play with it is the idea of inference, basically. So these are the 4 points I'd like everyone to take away. So when you're inferencing, you're going to be somehow loading the model. You'll be pre-processing your data in a way, so you'll be somehow packaging your data so that it can go through the model. There's a lot of ways you might want to do this with audio. Obviously, the easiest way is to just stream it through. That's nice and simple. You will then run the inference. I like to think of it as like a V4 engine. I'm not going to go into the details of a V4 engine today. I can if you want, but not the workshop. And then we just interpret the output. So you can either stream the output out immediately, or so for example, you might want to add a bit more DSP to it. You might want to have your black box model for your machine learning model and then do something else with it. So this is like a nice diagram I like to show people quickly to just do training versus inference. Training is something that you see a lot of, when you Google machine learning, I feel like you get a lot of training just straight out of your Google search, and it'll be go to TensorFlow, go to PyTorch, create a model. But obviously inference is just as important, and obviously that's how we make our products and how we get sound and stuff. So yes, you can see with training, you start with collecting and preparing your data, you train your model, you test your model. These little lovely diagrams you can sort of call forward and back propagation. And then with the inference, you're just running through. Brilliant. So please feel free to gloss over this. I just wanted to add a little bit about inference in production audio because we're at an audio conference, right? We do have to consider sometimes, sometimes with models in audio, you have to consider how long it's going to run. If you're doing offline processing, obviously not. We're in a Python environment here. We're not thinking so much about real-time safety and stuff. What you'd want to do is export this to C++. So, you're doing everything from scratch in C++. So you want to think about audio loading and streaming. You kind of want to avoid those memory bottlenecks because otherwise you'll get clicks and pops and stuff. You've got to think about your buffer size and stuff. And you just kind of want like a latency-aware code structure generally. So you want to think, as you're making your lovely Darbuka drums synth to go out that looks like a push, you want to think about the fact that there's going to be latency. Anywhere there can be latency, just have it in mind. And this generally comes from like unbounded execution times. So like any allocations, any garbage collection, things like any locks, obviously, that's going to cause issues. But these are only things to think about in production code. So don't worry too much. This is a prototype today. We did it in Python, so it's beginner friendly, obviously. So yeah, I want to just sort of reiterate what Anna explained about an hour ago. This is how we're interacting with the latent space. We're doing encoding, decoding, and forward passing. So we're taking our input data, we're taking our audio stream, we're running it through the model, with our forward pass, and then we're decoding it back into the original space. So it's like, yeah, so you can think of it as like a four-dimensional graph thing. I've been doing this in all of our calls where we're trying to figure out how we're going to explain it. It's not like a linear representation of audio. It's not sort of, we're not going X, Y, A, and B in a sort of programmatical way. It'll be sort of predefined in the model. And yeah, so encoding, as we've said, I promise there's an underscore there. I'm not chaotic. You just can't see it. It's not just latent space representation. That would be awful. It just wouldn't work. Yeah, so this is like often used to involve some form of compression or feature extraction. For example, in an autoencoder, the encoder part of the model compresses the input data into a lower dimensional latent space. So one problem with machine learning we see is if you pass in all the data, it's going to take ages to process. So like you might see it a lot. The good example is like in image processing. When you start with image processing, you'll see that they'll start with a high res image and they'll just sort of slowly compress it down so we can get something out of it quicker. Our forward pass, this is where the magic happens. This is when you turn the throttle on your V4 engine. And this is where we get input audio doing something. That produces our output. And then we decode because we want to bring it back out from the latent representation and we want to bring it back to audio. And this will, reconstruct the original data via the representation. So that's how we're going from a harp, we're going into this four-dimensional space, and then we're coming back to not sounding like a harp. We're running this by embedding it using a Python JIT. Please don't worry about this graph. I just couldn't not include it. It was like, I saw it and I was like, wow. And I would implore people to read this article that I've linked in the bottom right because it does a really good job of explaining JIT. The whole idea here is that so we can stay in the Python environment. As you can see, we've got like a nice red square around it all. We don't need to worry about it so much. The nice thing about JIT is that it's like, as a compiler, it's sort of, it looks at what parts of your code path sort of have bottlenecks. It does this in real time. So it's like just-in-time compiling, basically. So let's have a look at applied transformation. It's quite simple. So I've written this function in a way so that it is as simple as possible to explain. This is like where the magic happens. This is like where we're actually running our inference. So this first line here, this torch.setGrad enabled, that is a feature that we need when we're training because we need to be able to talk with the machine learning model. We need to be like, hey, you want to get closer to the right answer. So this gradient enable allows the loss function to sort of feed back if you know what that means. We'll go through this later, obviously. But that's why it's set to false now, because we're inferencing. We don't need that sort of backwards loop through. So we're making a tensor here. That's like a nice word that machine learning people like to use for multidimensional arrays. I've grossly simplified that there. Thank you very much. And then, so what we're doing, so we're making an instance of our tensor, our ultimate dimensional array, and then we're reshaping it into the shape that we need to go through the Rave model. And this looks like a 3D array, basically. So we've got like one element, all of the buffer. And that's how we sort of shape our input. So you wanna just handle that as you need. And then we encode. And this is where this encode happens. So at this point, we've still got our input harp data. This is when we want our latent coordinates. This is where we want our X, Y, and A and B, whatever mathematical term. And this is when we decode back. And then what we're actually returning back into our array is the decoded version. So this set latent coordinates is where we're running our inference, basically. Brilliant, okay. Let's take a quick break. I want to hear people playing with it. I want to answer any questions that anyone's got. Are there any questions quickly now before we take a quick break? Nailed it. Brilliant, okay. So everyone have a go. See what you can make. Please give other WAV files to it. I want to, let's start discussion about what files you might want to feed into this Rave model. There are other models you can play with as well. I'm not sure if we've got, no, we haven't got the tab open, so I'm not going to play with Yulia's laptop. Yeah, so should we say 15, 20 minutes? Does that sound good? Yeah, brilliant. Okay, so have fun, everyone. And we'll be back soon to do some training.
Okay, I guess it's time to resume. Already? Okay, cool. So now we'll be training our custom interactions to control the generative model. So again, first we'd like to set the scene and show you what the end goal is, what it will look like. We'll probably spare each other playing the audio this time. Just show you how the interactions change how your gesture can change the sliders. Pauline, can you do the demo for us?
So for the next part of the workshop, we will be controlling the controls. So we have this kind of pad on the right, and we want to train our application the way that when we move our mouse like on this trackpad, we also change the faders, and also change the sound, but just instead of the faders, we will use basically gestures. The problem here is that we have 4 sliders, but basically on the pad we only have 2 dimensions, and so we need to train it to understand what position on this trackpad means what position with faders. And so in this application, you see in the bottom 3 buttons / inputs, and the first one is training. We can turn it on. And also there you can see there's like a small text in the bottom, and it explains what is happening. So, for example, I need to give it a few spots, like which fader position means what. And for example, if I set it something in, I will do it a bit random, but you can be creative about it and set it the way you like. For example, I would say that this is something like the center, and you also see in the bottom it explain how we mapped it. So like we see the position on the sliders, and we see the position on this trackpad. And for example, I will change it, and we'll say that this is somewhere on the bottom right corner. And I will do this just a little, a few more times. It wouldn't look too nice for me because I'm not thinking too much about the system, how it should be. But yeah, I've set a few dots for training, and then I push I press the second input, which will train it, and you see that the training has started. And when it's finished, it will just say that the training finished. And after that, you set it to the third option, where you finally can control it. And as you can see, I'm moving around it, and it changes the position of the faders as well. And if you turn the audio on, you will also see the sound changes as well, like we did it before just with faders. It's it's a bit random for me right now because, as I said, I was setting it a bit random. But yeah, you can think of the system that you think works the best for you. It makes more sense, and train this model to understand the gestures on the right. And Sohyun will talk after me about regressions.
Okay, hello. I hope you're all enjoying the workshop so far. So with me, we'll go behind the scenes of the demo we just saw. So what was the demo showing? The demo was all about the training a regression neural network model based on the input and output data that you created yourselves. So here's the word like regression, neural network model, data, and training in this sentence. We will start with some basic concepts and definition of this terminologies first, and then we'll dive into the purpose and principles and process of building and training this regression neural network model. So what is regression? We want to take a trip back to the 19th century. So there was a statistician named Francis Galton who studied how parents and children's height relate to each other. He noticed that while kids' heights are influenced by their parents, they tend to regress toward the average height of the general population. So Francis Galton discovered a statistical trend in the relationship among the heights of parents and their children and the general population. If we could represent this trend mathematically, like let's say here with a certain function, it would be possible to make a reasonable prediction about a child's height based on the height of the parents and the population average, even if the child hasn't fully grown up yet. And this is actually where the term regression came from, and it became the foundation of what we now use in machine learning. Today in machine learning, like regression helps us predict a specific number based on the data patterns or the data trends. So again, when we analyze a regression problem in machine learning, what we are really doing is finding a trend between certain factors and the corresponding outcomes. And the goal is to define this trend as a mathematical expression, or I can say the mathematical model, so that we can use this mathematical model as a system to predict an outcome based on any given input. So we can start with very simple example here that we can analyze with regression. So here is the x-axis is daily average temperature and y-axis is ice cream sales. So if we gather the data on these over a large number of days, we can identify a trend from the data pair. And based on this trend, knowing the average temperature for any given day would allow you to make a reasonable estimate of how many ice creams are likely to be sold. And this, of course, this wouldn't be a perfectly exact prediction, but at least it gives you like idea based on the general pattern in the previous given data set. But actually, this ice cream example is pretty simplistic. What I mean is there's only one feature in input data and also one feature in output data. In reality, there could be many factors that influence the output. For example, humidity or whether it's a weekday or weekend, and many more. Also, there could be multiple output features to consider based on the input factor. In this example, however, we're only dealing with each pair of a single input feature and a single output feature. And also, the relationship between the input and the output can be drawn as a simple linear line. And it's easy to understand because the hotter the weather is, the more likely people are to buy ice cream. Yeah, so it's just proportional. And if you want to find the mathematical function of this linear line, it won't be too difficult. Like, it would be the, oh, sorry. Yeah, like y equal ax plus b, where a is slope and b is y-intercept. But however, in real life, when we analyze a regression problem, when we try to predict the value based on the trends given between given data pairs, the shape of the trend can get much more complex than this linear line. So in real life regression problem, each input and output can have multiple features. Here's only 3-dimensional. There's 2 features input and 1 feature output. And also the trend shown by these data pairs might not be a simple straight line on a 2-dimensional plane, but they can take on more complex curved and winding shapes across multiple dimensions, or even way more complex than this one, like a chaos, so you can't easily pick up as a trend. The point here is these complex nonlinear patterns with multidimensional input and output features can be so intricate so that it's nearly impossible to capture them with a single mathematical function or any simple mathematical expression. And here, that's why we use neural network to tackle this issue. In machine learning, there are various mathematical methods to create our mathematical model that describe the data patterns, but we specifically use a multi-layer neural network because it's particularly effective at capturing the nonlinear and complex and sometimes really random arbitrary tendencies in the data. Using a multi-layer neural network structure, we can analyze patterns not only in a common sense way, like we saw the ice cream example, but also recognize patterns in much more random data distribution as some non-linear trend. But how? I promise I'll go into more detail about what neural networks are and how they're structured and how they're able to model nonlinearity. But just before then, let me walk you through the kind of input and output data pairs we'll be using to design our regression neural network model. So as we saw in the demo with Pauline, we're creating a system that controls 4 sliders based on the mouse pointer's position on the XY path. And these 4 sliders are the latent space controller. Here, the relationship between the position on the XY path and the 4 slider positions is something that we define ourselves. It means like we're creating the data pairs needed for our regression neural network model. So for example, if I want to match the 4 sliders configuration in certain position, when your mouse pointer is at a certain point here, that creates one data point with a pair of input and output. And we can think of like how many features are included in one data point. For the input, only one point requires both on x coordinate and a y coordinate. So each input data has 2 features. What about the output? For each input defined by 2 features of an xy positions, there are 4 corresponding sliders values. So each output data has 4 features. So yes, again, one data point includes 2 input features of xy coordinates and 4 output features of sliders position. Also, I want to mention that after this one, when we're gonna cover this part in Jupyter Notebook with Julia, we're also gonna use a randomly generated data set made by Harriet. So what I just explained about is for the demo in the application. So our goal with neural network is to gather a lot of this data point and come up with a mathematical model that best captures the nonlinear and arbitrary patterns shown by these data. Then we can use this mathematical model as a system that takes any given input, which is any point on the XY path, and predicts the corresponding output values, which are for sliders' positions. And let's see how a multi-layer neural network model can build a model that really captures the nonlinear patterns in multidimensional data. So here's a visual representation of our regression neural network model. The first two blue circles on the left represent the two input feature values. So one for X coordinate and another one for the Y coordinate. And so many lines between the blue dots. These lines connecting the circles represent some mathematical operations. And the 32 circles in the middle represent the intermediate value that result from passing the input values through a function after the initial mathematical operations. And why it's 32? That's a number we choose. Because having a sufficient number of nodes here helps capture the complex patterns in the data more effectively. Finally, the 4 circles on the right are the final values obtained by applying further same mathematical operations to the intermediate value. And these represent the positions of the 4 sliders, which are the latent space controller we looked at earlier with Anna. So we actually already know the exact value for our inputs and outputs because they come from the data we've collected. And what we've done here is to set up a system of multiple mathematical operations, the neural network. And what we're going to do is to specify the values of the parameters within those operations. So now take a closer look at the individual part of the neural network. Okay, so in our designed neural network, the operations that transform input values to intermediate value and intermediate to output values follow the formula here. And to give an example, each input value, the x1 and x2, is multiplied by a unique weight 1 and weight 2, and then summed together with a bias term b. And this resulting value is sent to the first node in the intermediate node. So a linear layer means that this operation, this specific operation, is performed for every node without exception. So it's also called a fully connected layer or dense layer. And so this network uses linear layers both in the transformation from inputs to intermediate values and from intermediate value to outputs. When we talk about weights, we know that each line has a unique value, but we don't know the exact values of it. What we only know is the total number of weights, since the total number of weights is equal to the total number of lines here in this linear layer. So we have a total of 192 weights here. Next, here's the activation function applied to the intermediate value before they're sent to the output layer. There are various types of activation functions, but in this neural network, we use the one called the rectified linear unit, or ReLU. As you can see in the graph, This function outputs 0 for any input value less than 0. So any values, any negative values from the input linear layer becomes 0 after passing through this ReLU function. And this means that in the next output linear layer, multiplying these 0 values by any weights result in 0. So effectively deactivating those nodes. On the other hand, the positive values pass through unchanged, activating only this value. And this selective activation allows the neural network to respond specifically to certain patterns that each intermediate node represents, and helping the network filter out unimportant information, or you can say noise, and effectively pass along only the key information. And finally, the intermediate values, after passing through the ReLU, are transformed into our four final output values through another linear layer. So it's the same process. Okay, so we've covered the simple regression neural network structure we'll be using. Now we want to find the optimized value for the 192 weights and 36 biases that make up our network. We call this process training. The more these values are optimized, the better the network will capture the relationship between the input and output value. Then we'll be able to improve the neural network's performance in predicting the output for any given input. So let's take a look at how training works step by step. First, we pass all the input data from our dataset through the neural network. And this is called a forward pass. At this point, we don't know what the values of the weights and biases should be. So the network only has a randomly assigned value for this parameters. And after passing through the network, we will get the predicted result. And of course, this result will differ from the actual output values in our dataset, because the key value, the weight and biases in the network are just randomly assigned yet. So the second step in training is to quantify this difference between the predicted output and the real output. We use the mean squared error function, which is commonly used for regression problems, to calculate this quantified difference, and we call it loss or cost. And this cost is the average of the square difference between the actual data values and the model's prediction. Also, when we pass all our input data through forward pass, we called one epoch. So at the end of one epoch, or batch is a subset of your whole data set, and we get to know the cost using the mean squared error function. And finally, at the end of each forward pass for an epoch or batch, we begin the process of optimizing the neural network parameters using the loss obtained in this process. And this process is called backpropagation. This term is named because the calculations are carried out by moving from the output layer back to the input layer. And here's how the process works. So the first, we differentiate the loss function with respect to the neural network's output to obtain the gradient rate of change for the final output layer. Next, using this derivatives of the loss with respect to the output, we calculate the partial derivatives of the loss with respect to each weight and bias, so our parameters in the output layer. And this allows us to understand how each parameters in the output layer affects the loss function. Then we take this gradient calculated at the output layer and propagate it to the previous layer by calculating the partial derivatives of each parameter in this layer. We find the gradient for this layer as well. So doing backpropagation is by moving from the output layer back toward the input layer. We determine how much each parameter across all the layers affects the cost. So once the backpropagation process is complete and gradients are obtained for all parameters, we update the neural network's parameter using gradient descent. The formula for gradient descent is as follows. Here, theta represents the network's parameter, such as weights and biases. L is our loss function we just saw, and dl over d theta is the gradient of the loss function L with respect to the parameter theta. And finally, alpha represents the learning rate, which controls the step size of each parameter update. With these adjusted parameter values, the network proceeds to the next epoch, repeating from the forward pass to further optimize the parameters based on the updated loss value. And the final phase of training is essentially the recognition of when training is complete. As we repeat the forward pass across multiple epochs, we observe the loss decreasing. When this decrease becomes insignificant, meaning that further training doesn't seem to improve your network's performance, we can conclude that the model has found optimized parameter values, and we finally can end the process of the training. So, yes, we've covered the theoretical part of our regression neural network model and the overall process of training. So now Julia will demonstrate the implementation of this process within a Jupyter notebook. Thank you.
For everybody who has not please just run git checkout main. And this will give you access to the whole workshop because we removed the spoilers for the first part. Cool. I would try it like this. Cool. Whatever. Yeah, and I think I don't have any slides. Oh, cool. So that's basically my contribution here. Git checkout main, open the Jupyter notebook. We can open it by running Jupyter notebook again, which should pop up the notebook in your browser. Bleep, bleep. There we go. I'm opening the playgrounds file again. And now we can go to the second part. Alrighty. So I guess first of all, just like importing all the stuff that we'll need. It's a similar again. We're just like accessing the core of the Flask app. So bit winging it here. But yeah, so first of all, we can start by generating our model. Cool, that's the model class. You'll see more in detail later in the code. And we can set the layers of this model.
Yeah, exactly. So the layers here, as Sohyun has expertly demonstrated, so we've got two dense, linear, fully connected layers. You'll see these terms get thrown around. TLDR is the same thing. we can argue about that later. But basically what's happening is like a matrix multiply. So we're not doing like any sort of convolution. So the idea here is so that we can train quite quickly. Obviously it's like a bit of a, basic thing. What you will generally see in training models is there might be a dents at the input and the output. That's sort of like a normal thing there. So we've just skipped all the like big layers because obviously we've only got 3 hours. And then in the middle here, you'll see this ReLU, which is the normalization activation function that Sohyun's already described.
Yeah, we can also, I can print out a quick summary.
Oh, nice. Yes,
Yeah.
so it's worth noting as well. So depending on which API you're using, obviously we're using PyTorch. If you're using TensorFlow, you don't actually have to define the ReLU. It will be part of the, say, like the layer previous. So it'll be like an argument that you pass in. This varies from, API to API, just something to note. Yeah.
Cool.
So you can see, should we talk about the parameters, obviously? You can see the sort of shape that was sort of shown on screen here in more of a printout way. Obviously, the target for the output is 4 coordinates. We want X, Y, A, B. So we're doing some multiplications. We chose in 32 as an arbitrary number of sort of values to have for the matrix multiplication. And then what we're outputting there is the 4 values that we want to map to the sliders. And that's how it's all working.
Alrighty, we can go to the next line. By the way, I don't know if I mentioned it. To execute the lines, you press Shift-Enter. I'm sorry, I should have said that earlier.
We're only 2 hours in. That's
only 2 hours in. That's fine. It's just like sometimes you're like, oh yeah, I'm doing this, blah blah. It's just like the things, the essential things that you forget when you've been doing it for ages. Cool. Oh no. So we have here. No, but that's a prepared error. So it's a part of the presentation. So the XY control is like a kind of like a helper class that will set us up or interact with a model, but it does need an audio engine. Since I restarted the Jupyter notebook, I need to restart my engine again too. So I need to execute this line again, and create an audio engine. I will do that here. So after executing this line, I go back down. This should work now. Yay. And so now this class helps us interact. It's not really...
Yeah, so the reason I made this XY control class is just so anyone who's in the GitHub repo right now, they've cloned it in the RVS code. The reason for XY control is just to make a real simple module that you could just look at and be like, oh yeah, that's like super obvious. You probably wouldn't get a class that was like just for this in this case. But so everything that we're going to go through now is in xycontrol.py for anyone looking at the code in VS Code.
Yeah, cool. So now we're loading the data. I think this is actually loading the
Yes. Oh, yes.
data
So we've made some
being trained earlier.
Exactly. So
I'm not sure if it's like anyway.
Oh wait, is it not loading the JSON?
We'll see. We can also like basically. That's a nice thing about Jupyter Notebook. Let me just print it.
So what we're doing here is before the workshop, we wanted to say like, hey, what happens if we want 100 values? Obviously, we're not going to click around an XY pad 100 times. So what you can do is actually create this data beforehand, and you can create synthetic data basically. So you might see this .json file in the repo. I created that ahead of time. There's no correlation. I haven't spent time, fine tuning my 100 points. So we're just checking to see which one Jupyter Notebook is using right now.
Yeah.
No, it's the 100 values. There you go.
Yeah, cool.
Brilliant. So those values come from the .json file. You'll see it has like XY control and it is mapped to. So that's basically training data, and that's how you create synthetic training data. You might need this if you don't have access to 3 hours of darbuka drums. I don't personally. So but in this example, because we're only mapping to XY, obviously we can just make those float values.
Yeah. Exactly.
Brilliant. So hopefully we'd get better. Well, hopefully we'll get good correlation with the sliders.
So this is our pre-trained or pre-prepared training data. I'll dump that. And now we can initialize the training components.
So this is our loss function, the best mean square error, basically.
Yeah.
So we're initting to infinity because the idea is we want to bring it back down to 0. So we start super high, and we want to iterate for each pass, each epoch. We want to get closer and closer to getting what we're expecting. So basically, what you're saying is, hey, this is the value you want. This is the value you're giving. This is how far away you are, and that's training 101, I guess. And that's what's happening in train. Oh yeah, brilliant.
Yeah.
It's like we planned for this. So this is basically a very limited version of what's happening in this def train 1 epoch here. We're sort of going against the loss function. We're trying to see if the correlation has changed. And it's all about that sort of forward and backwards back propagation. And that's how you sort of interact with the machine learning model.
Yeah. You want to see like go through the batches.
Yep. Run the forward pass, run the backwards pass, and So you'll see here, you might remember from an hour ago when I said this require grad. This requires grad function was something that was actually a bug until last week when we realized that we hadn't set it, which meant that our loss function basically means every time a pass was happening, it wasn't looking at the loss function. It didn't care that it was like the correlation wasn't getting closer. So it requires this gradient because it wants to see that it's getting closer. So you can set it up to be random, but I don't know why you'd do that in this context. So
Right, let's execute that.
Let's execute that,
Now.
Brilliant. And this is running the loss, checking the weights, and it's adjusting the weights. So the idea being is it's trying to adjust the weights to refine down to what we would like to get out of it.
Yeah, so basically now we trained our model. In the app, it will be automatically set here. So to get our, basically to get the XY control into the state where it can process coordinates, we got to set this. And now we can make some noise this way. So I will start the audio engine again. Nice, I've set the loop. Oh, the sound is better.
Sounds so much better. Wow.
So now I set the transport. And as opposed to before, so this is like a leftover from the app for the app interaction. We can ignore it here, but we can set these two coordinates, and this will use like for example 100, 100. We'll make some noise. And it's basically similar to what happens when we run the flask gap.
Exactly.
So I will just show that quickly.
So the idea here is so the sliders that we introduced previously, the idea is that you're controlling those sliders via this XY control pad that you will see on screen shortly. The idea behind this is the fact that it can be any input. It doesn't have to be like an XY pad. It could be our original plan, but we had to shrink things down to do like video capture. So we take like a video stream and say, moving your hand, you could map that XY space. So exactly. So as you can see here, we've got this like lovely pad. Julia's quickly running through the training, starting the loop. And you'll see as she moves around the pad, the sliders are changing. So this might be a way, you might want to do this like say in live programming. If you've got like some form of accelerometer, you can move around or something like this. It's just a fun way to play with it, we find.
All right, so
if you're planning on training this yourself, which I'm hoping everyone is, I would recommend that when you're training in sort of this scenario, you want to go into the data gathering mode here, move your sliders to whatever correlation you want. I'd say between 10 and 20 points is a good starting point. Obviously, if you want it to just be random, just go ahead and smash the mouse around. Like, I love doing that. And you'll find some novel sounds, hopefully. You'll find it interactive. And as you can see, we've got this like little nice output screen. You can see the XYs changing the coordinates that are here, except they're not changing because you're on generate new data.
So just to quickly add some more points here.
Yeah.
Bloop.
You're doing like a, nice.
I don't know what I'm doing. So I'm apparently, if our training is good, like in the bottom left corner, it will be all up. On the top right, it will be all down. No, the other way around. All down on the bottom left. Well, we see. And somewhere in the middle, it'll be at a diagonal. And somewhere here, it'll be like alternating. Let's see. Let's just try.
Exactly. And so the idea here is that you can add, say, more layers if you want better correlation and stuff like that. So, hey, look at that. That's pretty good.
Yeah.
Hey.
Oh, well, so this would be all top. This would be all bottom. Oh, man, it works. Cool.
Yeah.
Yeah, so quick recap here. So we've got not one machine learning model, we've got two. We've got the Rave model, that obviously that's what we sort of discussed the inference. And then we've got this XY control, which is the model that we're training in, live. You can save the model, obviously. We haven't included any methods to save it because obviously we're just training it every single time. But what you could do is then save that model and do what we did with the rave.py and load it into memory, and just have to play with. So yeah, that's our lovely demo. Thank you very much.
I mean, if we have a bit of time, we could try out different sound files too.
Yeah, we can.
If you have time, we have time. Okay, cool.
Let's do it. Yeah,
Let's do it.
Yeah. Please feel free to stop playing with it.
Yeah. So let me just restart the notebook because I already restart the kernel because I already created the audio engine. Also, still because it's actually going through the Flask app, you don't actually have to create it multiple times. Yeah. But so I have this. I have this beautiful thing that recording that I recorded in my holidays, which I think is called.
Where did you go?
I hope you can guess.
Okay,
So the audio file is called More Cowbell. And let's try it with a drum model. And now we have the More Cowbell.
It's giving Europe.
Yeah.
Giving Europe.
And now we can try to transform this.
Hey, yeah. We can't hear it on stage because the monitor's that way, but...
Yeah. I can change the coordinates again. So I will spoil this. I was in the Alps. And we can also try a different model. So let me restart the kernel again. I earlier downloaded the... I think I earlier downloaded the vintage TS. I tried that on a few samples before.
Oh, nice.
And I do have I don't know what it is. I found this. I don't know what this is. I think it's either the bass thing or a bird thing. Let's see. Or let's just try it out.
A sentence I didn't think I was going to hear at ADC. It's either a bass thing or a bird thing.
I mean, this is it. I've been invited here, so it had to be expected.
That's true.
Let me clear my output so I don't get confused. I find that very helpful because then you can see which ones have been executed before. So okay, let's see what that is. Oh yeah, it's a base thing. So now I can apply this this model.
Lovely. Very nice.
Which is like the vintage. I think like the vintage sound output is like automatically adding like some vinyl effects.
Right.
It always gets like some vinyl crackling.
Nice.
And again, if we go back, train our model. We can also again. Bloop. Let me execute that. Change basically the coordinates that we'd receive through the XY pad as in the Flask app. So, yeah. That does not work very well.
Well, that's the joy of playing with the XY is you find
Yeah.
something that you like and you sort of
find
go
some sound
towards
that
it.
you like. Yeah.
Exactly.
All right.
Fantastic.
So that would be the Jupyter Notebook contribution for today. Let me stop this.
What time is it?
Cool.
We've got So we've got half an hour.
Yeah.
Should we have some time to train, get everyone training? You'll see that the training obviously is happening nearly it's happening in like 10 seconds. It's quite quick. So we're hoping that means that everyone can train, give it a go. I'm sure there'll be more Python issues that we'll need to run around and fix. Let's do it. Let's try it.
Sounds good. And then at the end, we have a small recap.
Yeah, we've got like a 10, 15 minutes of recap, go through what we've learned, what you might want to do with this going forwards, and why this is a prototype. Okay, lovely.
Cool.
Thanks, everyone. Let's do it.
All right.